Hi everyone, I'm Yu Yao from Department of Atmospheric Science, University of Illinois. Today my topic is about quantifying the effects of mixed-state on aerosol optical properties. So aerosol mixed-state describe the distribution of aerosol properties across a population of particles. And different particle species have different refract indices. And in the real environment, particles are usually a mixture of non-absorbing and absorbing species. So it's important to represent the aerosol mixed-state to get the correct optical properties. A study in 2005 shows the changes of air temperature if assumption used for aerosol mixed-state. In internal mixture assumption, each particle has only one species, and for internal mixture, all the particles are the same composition. And we can see from the map, uncertainty in direct radiative forcing due to the mixed-state assumptions leads to significant difference in the temperature response. However, models use assumptions for aerosol mixed-state. For model and section model are commonly used in regional or global models. In model, particles in the same mode have the same composition. And in section model, in each size bins, particles have the same composition. And we know it's not the true case. In current research, we use a particle zone model, PALM-C, which can trace particles individually and has no assumption of compositions. As for the particle shape, we do not want to go to detailed representation, so we use the mixed theory with shell core configuration. And the question we want to focus is what are the errors of aerosol optical values if internal mixture assumptions are used in the models? In order to solve this, we use a mean-state chi metric developed by Professor Raymond and West in 2013. We group the species to two large groups, non-absorbing species and absorbing species. And the chi is a ratio of the average particle diversity and bulk diversity. As we can see from these three populations, they have the same total species mass and the bulk diversity is the same, but the species distribute differently among the populations. For population A, each particle has only one species, so the average particle diversity is 1 equal to chi 0. They are externally mixed. For population C, species evenly distribute among the three populations, and the average particle diversity equal to the bulk diversity, resulting in chi equal to 100%. And population B is the interim state between A and C, so the chi is between 0 and 1. Then we use Latin cube sampling to create 100 scenario libraries. For each scenario library, we vary the environmental variables, include relative humidity, temperature, mixing height, and also the gas emitting rates, including sulfur dioxide, NOx, ammonia, and VOC. And also we change the emitting rates of different aerosol species and also the initial aerosol size distribution. For each scenario library, we use 10,000 computational particles, and we have 25 hours for each scenario. So total 2,500 particle populations are simulated. Since we do not include urban dust and sea salt, so our cases are close to urban environment. So this is a mass distribution of the scenario libraries, and we find our libraries have a wide range of mass concentration, from clean urban environment of total dry mass less than 5 microgram per cubic meter to polluted environments with total dry mass larger than 20 microgram per cubic meter. And this is an optical mean state histogram. And we find most populations have mean state larger than 60%. In order to recap what the chi means, I take out two populations. One is chi equal to 43, the other is chi equal to 87. And we can find with higher chi, particles look more similar and more internally mixed. And this is a single scattering albedo histogram. We find most of populations have SSA larger than 0.8. This is consistent with what the AirNet observed. So according to a study by Levy in 2007, they divide the particle into three types: absorbing particles with SSA around 0.85, and moderately absorbing with SSA around 0.9, and non-absorbing with SSA around 0.95. And our scenario libraries are quite representative of all these three populations. In order to quantify the changes due to intermixture, we take the dry particles from the reference population and we do composition average. And let all the particles in the same mixture. We preserve the total mass of each species and also number size distribution. We calculate the cross-section of each particle at wavelength 550 nanometer and divide by the computational volume, and we get the ensemble absorption. And in the end, we want to quantify the changes of ensemble absorption due to composition average assumption, the internal assumption, intermixture assumption. And this is the ensemble absorption correlated with optical mixing state and colored by black carbon mass concentration. And we find for most populations have higher mass concentration indicating higher absorption ability. And this is error after internal mixture assumption used. And we find most populations are overestimate with internal mixture assumption. And the range can be -8% to 115%. In order to configure what happens when we do composition average, we summary 4 conditions when we do composition average. For type A and type B, after composition average, we can see larger core and then result in increase of the absorption cross-section. And type C and type D, the decreasing core will lead to decreasing absorption cross-section. So the total absorption ability of the population is determining how many particles have larger core and how many particles have small core. And then we take out 3 populations with the same kind but different absorption error. Population A with -5% and population B with positive 47% and population C with positive 79%. So this is a particle absorption cross-section before and after composition average, and we can find the particle cross-section can increase or decrease. And for population C with the largest overestimation, they have more particles, have higher cross-section after composition average. And we find, to further explain this, we make the plot of the core size distribution, and we find for population A, which has a negative effect after internal mixture, is because more particles move from larger core to small core. And for population B and C, which you can see the increase of the absorption is due to the increase of the core size distribution. So in summary, aerosol mean state are important for calculating aerosol optical properties, and per particle absorption and cross-section can increase or decrease if we're using internal mixture assumption. And with internal mixture assumption, most populations are experiencing absorption overestimation, and the error can range from -8 to positive 115%. So that's for my talk. Thank you.